Now, the reason that I wrote this question for this episode of AP Chemistry Review and Practice is that we see this type of mistake made by students at the AP Chemistry reading all the time. So I don't want you to make this same mistake when you take the AP Chemistry exam. Take a look at this page of the AP Chemistry equations and constant sheet, and if you zoom in on the section entitled Thermodynamics and Electrochemistry, you will see this equation. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 6.7 to 6.9. As you can see on this slide, these topics fall under Unit 6 in the AP Chemistry curriculum, Thermochemistry. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 6.7, bond enthalpies. Here are some essential knowledge statements from the AP Chemistry course and exam description. During a chemical reaction, bonds are broken and/or formed, and these events change the potential energy of the system. The average energy required to break all of the bonds in the reactant molecules can be estimated by adding up the average bond energies of all of the bonds in the reactant molecules. Likewise, the average energy released in forming the bonds in the product molecules can be estimated. And if the energy released is greater than the energy required, the reaction is exothermic. On the other hand, if the energy required is greater than the energy released, the reaction is endothermic. Now let's move on to the practice for topic 6.7. This is question 1. In question 1, we are given a chemical equation that shows the breaking of a bond between 2 atoms of hydrogen, and the question asks, which of the following descriptions of the reaction represented above is completely correct? So we'll be looking at, in topic 6.7, how to calculate the value of delta H for a reaction. And to calculate the value of delta H for a reaction, when you use the bond enthalpy values, it will be the sum of the bond enthalpies for the bonds that are broken in the reactant molecules, because breaking bonds is an endothermic process in which energy is required or absorbed, and then minus the sum of the bond enthalpies of the bonds formed in the product molecules, and forming bonds is an exothermic process in which energy is released. Now, with respect to the sign of delta H, this goes back to topic 6.6, Introduction to Enthalpy of Reaction. The enthalpy change can be negative when heat energy is released, or positive when heat energy is absorbed. So to summarize, if you have an endothermic process, then the sign of delta H is positive. On the other hand, if you have an exothermic process, then the sign of delta H is negative. So we know that breaking a bond is an endothermic process, and if a process is endothermic, then the sign of delta H is positive. So let's go ahead and eliminate choices C and D in question 1, because we know that breaking a bond absorbs energy or requires energy. Breaking a bond does not release energy. And the correct answer is choice A, because the sign of delta H for the reaction is positive. That's an endothermic process, because breaking a bond requires energy. Now let's move on to question 2. In question 2, we are given a balanced chemical equation in which hydrogen reacts with nitrogen to produce NH3. And we can see that the change in enthalpy, or the delta H, for the reaction represented by this equation is negative 92 kilojoules per mole of reaction. We are also given a data table with some bond energy values, but this table is incomplete. There is a question mark for the nitrogen-hydrogen bond in NH3. And so question 2 says the following. Based on the bond energies given in the table and the value of delta H, or the change in enthalpy for the reaction, which of the following is the best estimate for the energy of one of the nitrogen-hydrogen bonds in NH3? So we will use that equation I had mentioned earlier, in which the delta H for the reaction is equal to the sum of the bond enthalpies for the bonds broken in the reactant molecules minus the sum of the bond enthalpies of the bonds formed in the product molecules. So the first thing that I notice on the reactant side of the equation is 3 molecules of hydrogen. So I will represent on this slide 3 molecules of hydrogen so I can keep track of all of the bonds that are broken in the reactant molecules. Now there's also 1 molecule of nitrogen, so I will represent a molecule of nitrogen. And moving on to the product side of the equation, I see 2 molecules of NH3, so I will represent 2 molecules of NH3 like this. Now you might be wondering that I have not included the lone pairs of electrons. If these were Lewis electron diagrams, they would be incomplete. But I'm choosing to simply focus on the structural formulas, the connectivity of the atoms, so I can keep track of all of the bonds that are broken in the reactant molecules and all of the bonds formed in the product molecules. Now that we have that information, let's go ahead and plug in the numbers that we know and then solve for the number that we don't know. So the change in enthalpy, or the delta H for this reaction, is negative 92 kilojoules per mole of reaction. So I will write negative 92 for the value of delta H, and then I see that the hydrogen-hydrogen bond in hydrogen is 436 kilojoules per mole. So because I have 3 of them, that would be 3 times 436. And I have 1 nitrogen-nitrogen bond in N2, so that would be 940. So these values will give me the sum of the bond enthalpies of the bonds broken in the reactant molecules. And now moving on to the bond enthalpies of the bonds formed, that is the number that I don't know. So I will just simply represent that there are 6 nitrogen-hydrogen bonds in these 2 NH3 molecules. Now that I have listed all of the numbers that we know, let's go ahead and do the algebra to solve for the bond enthalpy of the nitrogen-hydrogen bond in NH3. So the next thing that I will do is multiply 3 times 436 plus 940, and that gives me a value of 2,248. The next thing that I will do is I will add 92 to both sides of this equation. I will also add 6 times the bond energy of the nitrogen-hydrogen bond to both sides of this equation, and it looks like this. Now 2,248 plus 92 gives me a value of 2,340, but that represents the sum of 6 nitrogen-hydrogen bonds, so now I have to divide by 6. So 2,340 divided by 6 will give me the nitrogen-hydrogen bond energy, and when I do that math, I get 390. So the nitrogen-hydrogen bond energy is 390 kilojoules per mole, and that makes the correct answer to question 2, choice B. Now let's take a look at question 3, which is a similar type of question, but now instead of solving for the bond energy, we will be solving for the delta H for the overall reaction represented here. So in question 3, we are given a bond enthalpy table, and question 3 says the following. Based on the bond enthalpies given in the table above, which of the following is the best estimate of delta H for the reaction represented below? Again, let's keep track of our bonds broken in the reactant molecules and the bonds formed in the product molecules. So the first thing I notice is that there are 4 carbon-hydrogen bonds in that C2H4 molecule. I also notice that there is a carbon-carbon double bond. And I notice that there is a hydrogen-hydrogen bond. So these are all of the bonds that are broken in the reactant molecules. Moving on to the other side of the equation, there's only one product molecule, and that's C2H6. So I see 6 carbon-hydrogen bonds that are formed, and I see one carbon-carbon single bond that is formed. The next thing that I need to do is to use the data from the bond enthalpy in the table to simply do the math and calculate the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. So filling in the numbers, 4 times 413 for the carbon-hydrogen bond, and then 6 times 413 for the carbon-hydrogen bond. The carbon-carbon double bond is 614. The hydrogen-hydrogen bond is 436. And the carbon-carbon single bond is 348. Now I just need to do this math. So bonds broken minus bonds formed. That will be 4 times 413 plus 614 plus 436. And that works out to be a grand total of 2,702. And then I have 6 times 413 plus 348, and that works out to be 2,826. So the correct answer to question 3 would be 2,702 minus 2,826, and that works out to be negative 124 kilojoules per mole of reaction. So the correct answer to question 3 is choice A. And now let's take a look at question 4. In question 4, we are given information about a chemical reaction between chlorine and fluorine. It says gaseous chlorine and gaseous fluorine can react to form chlorine trifluoride gas as represented by the following equation. So in this equation, I can see that 1 molecule of Cl2 reacts with 3 molecules of F2 to produce 2 molecules of ClF3. And we are also given bond energy values for fluorine-fluorine, chlorine-chlorine, and chlorine-fluorine. Now, question 4 says, a student was given the table of bond enthalpy shown above and asked to calculate the value of delta H, or the change in enthalpy for the reaction, and the student set up the calculation as follows. Bond enthalpies for the product minus bond enthalpies for the reactants, and the student obtained a value of positive 798 kilojoules per mole of reaction. Now, as you're watching this video, if you say to yourself, but that's an incorrect method of solving this problem, well, you are right, this is incorrect. So in part A, it says the student's answer of positive 798 kilojoules per mole of reaction is incorrect. Identify the error in the setup for the student's calculation that explains why the calculated value of delta H is incorrect. Now, the reason that I wrote this question for this episode of AP Chemistry Review and Practice is that we see this type of mistake made by students at the AP Chemistry reading all the time. So I don't want you to make this same mistake when you take the AP Chemistry exam. Take a look at this page of the AP Chemistry equations and constant sheet, and if you zoom in on the section entitled Thermodynamics and Electrochemistry, you will see this equation. Now, this equation should not be used when you are doing a bond enthalpy calculation for topic 6.7. This equation should be used for topic 6.8, which is coming up a little later in this lesson. So this equation shows products minus reactants for something that is labeled as delta H with a subscript of F. So that subscript of F, the F stands for formation. And the enthalpy of formation is not, repeat, is not the same as a bond enthalpy value. So don't make the mistake that the student made in question 4. And now what I'm going to do is remind you that this equation, which is bonds broken minus bonds formed, this equation does not appear on the AP Chemistry equations and constant sheet. You just have to know this equation and know when to use it. And so now let's go ahead and solve the question for calculation. Let's go ahead and solve this problem in the correct way. So what I'm going to do now is focus on the bonds broken minus the bonds formed. On the reactant side of the equation, I see 1 molecule of Cl2. I see 3 molecules of F2. And on the product side of this equation, I see 2 molecules of ClF3. Now let's fill in the numbers from the bond energy table. So for the chlorine-chlorine bond, that would be 243. And there's only 1 chlorine-chlorine bond that is broken on the reactant side of the equation. I see 3 molecules of F2, so there would be 3 times 159. And on the product side of the equation, I see a total of 6 ClF bonds, so that would be 6 times 253. So here is the math involved for this question. The delta H is equal to 243 plus 3 times 159, and then minus 6 times 253. Now, when I do that math, I get 720 minus 1,518, which gives me an answer for delta H of negative 798 kilojoules per mole of reaction. And if you look at what the student did wrong, the student got a value of positive 798 kilojoules per mole of reaction instead of negative 798 kilojoules per mole of reaction. So the student used a setup for the calculation of delta H that involved products minus reactants, instead of setting up the calculation as total bonds broken minus total bonds formed. So their final answer for delta H has the correct magnitude of 798, but the wrong sign. So again, that's a very common mistake that students make on the AP Chemistry exam. So please don't make that mistake if you're given a bond enthalpy calculation problem. Now, in question 4, part B, they simply want us to calculate the value of delta H and show the correct setup. So the correct setup would be bonds broken minus bonds formed, and the correct answer is negative 798 kilojoules per mole of reaction. Well, I hope that that all makes sense to you, because now it's time to move on to the review for topic 6.8, enthalpy of formation. So the essential knowledge statement from the AP Chemistry course and exam description says, tables of standard enthalpies of formation can be used to calculate the standard enthalpies of reaction. So the delta H for the reaction would equal the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation for the reactants. And now we are ready to move on to the practice for topic 6.8. This is question 5. In question 5, it says propane, which has the chemical formula C3H8, reacts with oxygen gas to produce carbon dioxide gas and water vapor according to the following equation. And you'll notice that in addition to the balanced chemical equation, we have a table with standard enthalpy of formation. So these values are not bond energy or bond enthalpy values. These are values for standard enthalpy of formation for C3H8, O2, CO2, and H2O. And the question says, based on the information given, the delta H, or the change in enthalpy for this reaction, is closest to which of the following? So we will use the equation that I mentioned for topic 6.8, which is that the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation for the reactants, that will give us the change in enthalpy for this reaction. So I will start with the product, which is carbon dioxide. Now there is a coefficient of 3 next to the carbon dioxide, so that means I will take the number for carbon dioxide, the negative 394, and I will multiply by 3. The next product that I see is water, and I also see a coefficient. This is a coefficient of 4. That means that the math involved will be 4 times the number for water, which is negative 242. So 4 times negative 242. Now, when you're setting up these calculations, make sure to pay attention to positive signs and negative signs to avoid errors in arithmetic or algebra. Now that I've focused on the products, I'm going to move on to the reactants. The first reactant that I see is C3H8, so that would be a value of negative 104 for the enthalpy of formation. And then the next reactant that I see is oxygen gas. That would be 5 times the value for oxygen gas, which happens to be a 0. So by definition, the standard enthalpy of formation for an element in its standard state is defined as 0. Well, now that we have the setup, let's go ahead and do the math to calculate the change in enthalpy for this reaction. So it's going to be 3 times negative 394 plus 4 times negative 242 and then minus negative 104. And when I do that math, I get a value for delta H for the reaction, which is negative 2046 kilojoules per mole of reaction. So the correct answer to question 5 is choice A. Now let's move on to question 6, which is similar to question 5. But this time, we actually are given the delta H for the reaction. So we are given that the change in enthalpy for this reaction is negative 1,168 kilojoules per mole of reaction. So what we don't know is the question mark in the table. So question 6 says, based on the reaction and the data table shown, what is the value for the standard enthalpy of formation for the substance N2O4? Let's go ahead and use that same equation so that the delta H for the reaction is equal to the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation for the reactants. We'll plug in everything that we know, and then we'll solve for the one thing that we don't know. Now, the first product that I see is nitrogen, and I see 3 moles of nitrogen, or 3 times that value, but that would be 3 times 0. The next product that I see is water vapor. That would be 4 times the number for water, so 4 times negative 242. And now that we're done with the products, let's move on to the reactants. The first reactant that I see is N2H4, and I see a coefficient of 2, so that would be 2 times positive 95. And then the other reactant is the one that we don't know. That would be the enthalpy of formation for N2O4. So we don't know that value yet, and that's what we have to solve for to answer question 6. So the delta H for this reaction is listed as negative 1,168. And if I do the products minus reactants, that would be 3 times 0 plus 4 times negative 242, which is negative 968. And then on the reactant side, that would be 2 times 95, which is 190. And the delta H of formation for N2O4, which we don't know at the moment. Now, pay close attention to signs, because it's going to be minus the sum of 190 plus this unknown quantity, and you'll notice that I distributed that negative sign to the 190, so that would be negative 1168 is equal to negative 968 minus 190, and then minus the enthalpy of formation for N2O4. Again, don't make those algebra errors, which might be common if you're rushing or going too fast. So the next step in the process is to solve for the value for the enthalpy of formation for N2O4. And when I do this algebra, I get negative 968 minus 190 and then plus 1,168. So my final answer when I do this algebra correctly is positive 10. Notice that the correct answer is choice C for question 6, but a very common and incorrect answer would be choice B, which is negative 10. So positive 10 is the correct answer, but a student that perhaps made an arithmetic error or an algebra error, they might have chosen choice B. All right, well, hopefully the answers to questions 5 and 6 make sense, because now it is time to move on to the review for topic 6.9, Hess's law. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many processes can be broken down into a series of steps. Each step in the series has its own energy change. And because total energy is conserved, first law of thermodynamics, each individual reaction in a sequence transfers thermal energy to or from the surroundings. The net thermal energy transferred in the sequence will be equal to the sum of the thermal energy transfers in each of the steps. These thermal energy transfers are the result of potential energy changes among the species in the reaction sequence. Thus, at constant pressure, the enthalpy change of the overall process is equal to the sum of the enthalpy changes of the individual steps. The following are essential principles of Hess's law. When a reaction is reversed, the enthalpy change stays constant in magnitude but becomes reversed in mathematical sign. When a reaction is multiplied by a factor, C, the enthalpy change is multiplied by the same factor, C. And when two or more reactions are added to obtain an overall reaction, the individual enthalpy changes of each reaction are added to obtain the net enthalpy change of the overall reaction. Now let's move on to the practice for topic 6.9. This is question 7. In question 7, we are given 3 different balanced chemical equations. Each equation has a known value for the change in enthalpy, or the delta H. So I can see a delta H value of positive 11.3 for the first equation. I can see a delta H value of negative 571.6 for the second equation. And I can see a delta H value of negative 206.6 for the third equation. All of them have units of kilojoules per mole of reaction. Now, question 7 says the following. Based on the information above, the value of delta H for the following reaction is closest to which of the following? So this is a Hess's law problem. And what we need to do is make any necessary modifications to these 3 equations shown above so that when the modified versions of the equations are added together, they will produce the balanced chemical equation shown below. So the first thing I'm going to do is start with the reactant N2O5. So what I need is 1 mole of N2O5 to appear on the left side of the equation. So where can I find the N2O5 in the equation shown above? Well, it's right here. So it's on the right side of the equation, but I need the N2O5 to appear on the left side of the equation. So the necessary modification to that first equation is simply to reverse it. Now, when I reverse it, the sign of delta H will change. So right now it says positive 11.3. And when I reverse that equation, the delta H will become negative 11.3. Let's move on to the next substance. The next substance that I'm focusing on is H2O. Now I see 1 mole of H2O on the left, so I'm looking for H2O in the equations above. Well, there's the H2O. It's on the right, and it has a coefficient of 2. So the 2 modifications that I need to do for this equation is to reverse it, but I also need to change that 2 into a 1, which means I will multiply each of the coefficients in that equation by 1/2. Now I see that the delta H is negative 571.6, but when I make that necessary modification, which is to reverse it and multiply by 1/2, then the sign will change, and then 571.6 times 1/2 becomes 285.8. So there's my modified equation with coefficients of 1, 1, and 1/2 because I multiplied each of the coefficients by 1/2, and I reversed the equation so the sign changed. Now the next substance that I'm focusing on is the HNO3. So I need 2 moles of HNO3 to appear on the right side of the equation. So there's the HNO3. It's on the right side of the equation, but I need to multiply each of the coefficients in that equation by 2. So the delta H will change from negative 206.6 to negative 413.2, when I multiply each of the coefficients by 2, I also multiply the value of delta H by 2. Now what I'm going to do is simply draw a line underneath the three modified equations, and if I see any chemical that appears on both the left side and the right side of the equation in equal amounts, then I can cross off that substance on both sides of the equation. So the first thing that I notice is that there is 1 mole of hydrogen on the left, and there's 1 mole of hydrogen on the right, so I cross off the hydrogen. The next thing that I notice is that there is 1 mole of nitrogen on the left, and there's 1 mole of nitrogen on the right, so I can cross off the nitrogen. Now I see 3 moles of oxygen on the left, and on the right side of the equations, I can see that there's 5 halves and 1 half, and when you add 5 halves and 1 half, you get 6 halves, or 3, so that means that there is a total of 3 moles of oxygen on the right side, so I can cross off the oxygen. Now what remains is 1 mole of N2O5 on the left, 1 mole of H2O on the left, and 2 moles of HNO3 on the right. So it's exactly what I want. The answer to question 7 is going to be the following: negative 11.3 plus 285.8 plus negative 413.2. And when I do that math, I get negative 138.7 for the value of delta H for this overall reaction. So looking at the 4 choices in question 7, I can see that the correct answer is approximately negative 139 kilojoules per mole of reaction. So the correct answer to question 7, based on Hess's law, is choice C. Now let's take a look at question 8. This is also a Hess's law problem. And here in question 8, it says that reactions 1 and 2, shown above, can be manipulated to produce reaction 3. But this time, we're actually calculating the delta H for reaction 2. So it's going to be a similar question to question 7, but now we are given that the delta H for reaction 3 is negative 80 kilojoules per mole of reaction. We are given that the delta H for reaction 1 is negative 92 kilojoules per mole of reaction, and at the moment, we do not know the value of delta H for reaction 2. So that is going to be our goal, is to calculate the value of delta H for reaction 2. Now, the first thing that I notice in reaction 3 is that I need there to be 1 mole of chlorine, or Cl2, on the left side of the equation. So where do I see chlorine above? Well, there's the chlorine in reaction 1, but I need to multiply each of the coefficients in reaction 1 by 2. And if I do that, then the value of delta H will also be multiplied by 2. So the modified version of that reaction would be coefficients of 1, 1, and 2 from left to right. And the value of delta H will be negative 92 times 2, which is negative 184 kilojoules per mole of reaction. The next substance that I will focus on is the HBr. So I need 2 moles of HBr to appear on the left side of the equation. And when I find HBr in reaction 2, I notice that it's on the right side of the equation with a coefficient of 1. So the modification that I have to make to reaction 2 is it should be reversed, and each coefficient will be multiplied by 2. So the modified version of that equation will have a delta H, which is going to be multiplied by 2, and the sign of delta H will change. So as you can see, I'm showing that the delta H for reaction 2 is labeled as X. And in the modified version, which has been reversed and multiplied by 2, the delta H would equal negative 2X. So changing the sign and multiplying by 2. Now what I'm going to do is I'm going to draw a line underneath these 2 modified equations. And if there's anything that appears on both the left side and the right side of the equation, then I will cross off that substance on opposite sides. And all I see that needs to be eliminated would be 1 mole of hydrogen on the left and 1 mole of hydrogen on the right. Now, when I add equations 1 and 2 that have been modified together, that would be negative 184 plus negative 2x, and that would equal negative 80. So now I just have to do a little algebra to solve for x. So negative 184 plus 80 equals 2x. Negative 184 plus 80 is equal to negative 104. And if that equals 2x, then x equals negative 104 divided by 2, which is negative 52. So the correct answer to question 8, which is the delta H for reaction 2, is negative 52 kilojoules per mole of reaction. So that makes the correct answer to question 8 choice B. All right, there's one more Hess's law problem, and that would be question 9 in this packet. So what I see in question 9 is we have two reactions, and it says, based on the information shown above, what is the value of the delta H for reaction 3 represented below? So it's a similar process that we saw in questions 7 and 8. Let's go ahead and focus on how these reactions can be modified together so that when the modified versions of the equations are added together, it will produce reaction 3. The first thing that I notice is that I need 1 mole of solid iodine, or I2, to appear on the left. So in reaction 1, there is solid iodine on the left, but it has a coefficient of 1/2. So reaction 1 should be modified by multiplying by 2. And when I do that, then the delta H value will also be multiplied by 2. So negative 26 becomes negative 52. And the coefficients are 1, 1, and 2. So negative 52 kilojoules per mole of reaction. The next substance that I will focus on is, instead of solid iodine, I'm going to focus on gaseous iodine, which appears on the right. So I need there to be 1 mole of gaseous iodine, or I2, on the right side of the equation. Therefore, reaction 2, which has gaseous iodine on the left, needs to be reversed. And to change that 1/2 to a 1, I will multiply that equation by 2 as well as reverse it. So when I do that modification, negative 57 will now become positive 57. And then multiplying by 2, that becomes positive 114. So there are the modified versions of reactions 1 and 2. I will draw a line underneath the modified versions of the equations. Do I see anything that can be crossed off on both the left and the right side? And the answer is yes. There's a hydrogen on the left, hydrogen on the right. There's 2 moles of HI on the left. There's 2 moles of HI on the right. And so now the answer to question 9 would be negative 52 plus 114. And when I do that math, I get positive 62 kilojoules per mole of reaction. So the correct answer to question 9, based on the Hess's law manipulations, is choice D, which has a value of positive 62 kilojoules per mole of reaction. So the correct answer to question 9 is choice D. Now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice is that if you need more information on these topics and you would like more practice problems, you can review the information in my video for topics 6.6 to 6.9. My next piece of advice is what I normally say at this point in the lesson, and that is read the question carefully and make sure that you are answering the question that is being asked. And to make sure that you earn credit for your work on the free response section of the AP Chemistry exam, always show your work for your calculations. Remember that when you are setting up a calculation that involves a combination of mathematical operations and positive and negative signs, take care to avoid errors with arithmetic or algebraic manipulations. On the AP Chemistry exam, you may see a table with values for bond energy or enthalpy, and they have positive values, and the units are normally kilojoules per mole. For example, the bond energy of the hydrogen-hydrogen bond is 436 kilojoules per mole. And that would be the energy absorbed if you break that bond with a delta H of positive 436 kilojoules per mole. But that would also be the amount of energy released if that bond is formed. So the delta H would be negative 436 kilojoules per mole if that bond is formed. My next piece of advice is that a double bond is stronger than a single bond. and a triple bond is stronger than a double bond. However, mathematically, these are different values, that the bond energy value for a double bond is not exactly twice as much as the bond energy value for a single bond. So if I were given a double bond for carbon, that would not be 348 multiplied by 2. So a single bond has a bond energy of 348, but the double bond happens to be 614, and the triple bond happens to be 839 kilojoules per mole. So you should use the single bond, the double bond, and the triple bond as independent values that would be given to you on the AP Chemistry exam. My next piece of advice involves the equation that does not appear on the AP Chemistry equations and constant sheet, and that would be that the sum of the bond enthalpies for the bonds broken in the reactant molecules minus the sum of the bond enthalpies for the bonds formed in the product molecules, that will give you the value of delta H based on bond enthalpy values. Remember to use the coefficients from the balanced equation in your bond enthalpy calculations, and as I showed you in this lesson, it can be helpful to draw the structural formula of the reactants and the product molecules in order to keep track of all of the bonds that are broken and formed when you're doing your calculation of delta H from bond enthalpies. Now, switching from topic 6.7 to topic 6.8, a bond enthalpy value does not have the same meaning as the value for enthalpy of formation, which is in topic 6.8. By definition, the enthalpy of formation for a pure element in its standard state, which is conditions of 1 atmosphere and 298 Kelvin, would be 0. And on the AP Chemistry exam, you may see a table with values for enthalpy of formation for various substances involved in a chemical reaction. Now, this can be a number with a positive value, a negative value, or 0, depending on the substance. And the phase of matter of the substance is included because the value for the enthalpy of formation is dependent on the phase of matter. And the units are normally kilojoules per mole. So here are a few examples of enthalpy of formation values for elements and compounds. Some of these elements are 0. You'll notice that solid iodine is 0 because that is the natural state of iodine under these standard conditions, but gaseous iodine is not the standard state of iodine under standard conditions. That's why you see 62.4 for gaseous iodine as compared to 0 for solid iodine. So anyway, these are examples of enthalpy of formation of various substances. My next piece of advice is that if you are talking about a topic 6.8 type of problem, you should use the following formula, which does appear on the AP Chemistry equations and constant sheet, and that is that the sum of the enthalpies of formation of the products minus the sum of the enthalpy of formation for the reactants will give you the value for delta H for that reaction. Again, remember to use the coefficients from the balanced equation in your enthalpy of formation calculations. Now, with respect to Hess's law, with Hess's law calculations, be familiar with how the value of delta H is affected when a chemical equation is reversed. You would change the sign of delta H, or multiplied by a constant, you would multiply the value of delta H by that same constant. And when two or more equations are added together, the values of delta H are also added together. Okay, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 7.1 to 7.4. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.